So today we're starting chemical reactions, which is unit 4, and this unit is going to be a relatively quick one, I hope. We're going to talk about a few things you should already know, like physical changes versus chemical changes. So physical changes occur when a substance's properties change, but not its composition. In other words, if the chemical formula doesn't change, it's a physical change. Like if you melt an ice cube, that is a physical change. You're just overcoming intermolecular attractions. So examples include melting, freezing, forming or separating a mixture, like dissolving sugar into water, or separating a mixture through distillation, for instance. That's all physical changes. Now, the line can get a little blurry. For instance, you could make an argument that dissolving salt into water, which is typically described as a physical change because you're not forming new chemical bonds, you're just, but you could argue that you're breaking the ionic bonds in the ionic compound and you're forming ion dipole interactions. So you could argue that it does definitely involve changing some, making and breaking some chemical bonds, but you're not creating entirely new compounds when you dissolve, say, salt into water. And the properties of the salt and the properties of the water still remain unique and distinct. Unlike, for instance, when you take sodium, a silvery colored soft metal, and chlorine, a greenish colored poisonous gas, and you mix them together and you get salt. That's clearly a chemical change, not a physical change. So chemical changes, you get new substances, chemical bonds are formed or broken, and you should be aware of the signs that a chemical reaction has taken place. If heat or light are given off, or heat is absorbed, that's a sign of a chemical change. If a gas is produced, that's a sign of a chemical change. If you make a precipitate and you mix two liquids together and a solid forms, that's solid called a precipitate. That's a sign of a chemical change. And if there's a color change, that can be a sign of a chemical change. However, be aware that if you take red Kool-Aid and you add water and it turns into light red Kool-Aid, that's not a sign of a chemical change. That's a sign that you have diluted it with water. Okay. Now, the last thing we're going to look at for today is chemical equations. And you can use a chemical equation to represent physical or chemical changes. You can also represent them with particle diagrams. And chemical equations, as you already know by now, must be balanced in order to demonstrate the law of conservation of mass. Tomorrow, we'll start things off with ionic and net ionic equations. I just want to show you this one example. This is off the 2018 exam, where it says, student investigates the reaction of nitrogen oxides. One of the reactions in the investigation requires an equimolar mixture of nitrogen monoxide and nitrogen dioxide, which they produce by using the reaction represented above. The particle level representation of the equimolar mixture in the flask at the completion of the reaction is shown in the box at the right. In the box below on the left, draw the particle level representation of the reactant. That's the things on the left. These are reactants. This is your product. Mixture of NO and O2 that would yield the product mixture shown in the box on the right. In your drawing, represent oxygen atoms as nitrogen and nitrogen atoms as indicated below. So oxygens are white circles and nitrogen atoms are shaded circles. If we look at this, we can count how many nitrogens and oxygens we have. We have 1, 2, 3, 4, 5, 6, 7, 8 nitrogens, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygens. Well, each nitrogen was combined with an oxygen to start with. So we need to draw our 8 nitrogens. 1, 2, 3, 4, 5, 6, 7, 8. And each one of them was combined with an oxygen. 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 4 oxygens left over, and oxygens are O2 molecules. So here's 1, 2, and 3, 4. So in this box, you would draw 2 oxygen molecules, and then you would draw 8 nitrogen monoxides. And if you look at what happens, essentially, in this reaction, to get our product mixture, we have 1, 2, 3, 4 nitrogen dioxides are produced. 1, 2, 3, 4. While we also have 4 nitrogen monoxides that are left over. And this is going to be an important thing when we get into stoichiometry, which we're also going to be doing in this unit, where we're looking at relationships where you need twice as many nitrogen monoxides as oxygens to do this reaction in full. But we don't have that necessarily. We had, 4 times as many nitrogen monoxides as we did oxygens.